Hello, this is Mr. Gilmore with the 7.2 Angle-Angle Similarity lesson. Now, today begins our journey into looking at triangle similarity principles. So very much like back in our congruence chapter where we begin to try to find shortcuts to congruence with our triangles, we're doing the exact same thing today, looking for shortcuts in similarity. And today we're going to encounter angle-angle similarity. Now, before we get to that, we are going to need a postulate. So I start off with a question. Do you believe? Here's the question I'm going to ask you. Do you believe that we may take a polygon and scale it by a factor of our choice and thereby create a second polygon similar to the first? Well, I do. I feel that this is obvious, which means we're going to lean right into our very first postulate, known as the Polygon Similarity postulate. What we can do with this is actually construct a second polygon using a positive, essentially a positive quantity to scale our first polygon, then to create this second polygon similar to our first. So here's what this states. It says, given a polygon P and a positive quantity K, we may construct a second polygon Q such that the polygon P is similar to the polygon Q with the scale factor of K. In other words, I can take the sides of the first polygon P, multiply it by this positive value K, and it's going to then turn into a new polygon for us. We'll call that polygon Q, such that it will be similar to the first. So now here's the plan with our postulate. We are going to take this and build it into three phenomenal theorems. They are the angle-angle similarity, the side-angle-side similarity, and the side-side-side similarity. Now, today we are going to prove angle-angle similarity. And for future reference, we are going to actually skip the proofs of the side-angle-side and side-side-side similarity theorems. The proofs of these are going to essentially be identical to the proof of the angle-angle similarity. And so we'll see how angle-angle similarity unfolds today, and essentially we'll use the exact same idea to prove angle-angle as we would have with side-angle-side and side-side-side. So again, we're going to forgo the proofs of those two. So let's talk about what is angle-angle similarity. Now, for us, we can simply write AA similarity. I might shorthand it even as this angle-angle, and then just use our tilde symbol for the similarity symbol. So here's what it states. If two angles of one triangle equal two angles of another, then those two angles are similar. That is how simple the angle-angle similarity is, and also how powerful the angle-angle similarity is. All we need are two angles of one triangle to equal two angles of another, and we have similar triangles. Think about what we saw back in the chapter of congruence, where we had shortcuts to congruence. This is a shortcut to similarity. Now, here is the setup of our proof. Just like any good conjecture, we need to prove it. So we're given two triangles below, triangle ABC, triangle RST, such that angle A is equal to angle R, and that angle B is equal to angle S. We are going to prove that these two triangles are, in fact, similar to each other. So now here is the idea. We're going to construct a third triangle, and now we have the ability to construct similar polygons. We have our polygon similarity postulate. So here's the idea. We're going to construct this third triangle. We're going to call this third triangle X, Y, Z. Now we want this triangle to do two things, okay? It really is going to be a pretty clever trick that we're going to do here, clever strategy that we have to actually have this constructed third triangle do two things. The first thing that we're going to see is that this newly constructed triangle will be similar to our first triangle, triangle ABC. And we want this triangle XYZ to also be congruent to our second triangle, triangle RST. So in other words, we will have this third triangle essentially building a bridge between our two given triangles. That third triangle is going to be similar to one and congruent to the other. Now, what we can then conclude with this information we have is that triangle ABC and triangle RST will in fact be similar. And here's why. If one triangle is similar to a second, and the second is congruent to a third, then we've proven first and third are similar. If we think back to the previous worksheet when we introduced similar polygons, we actually proved this. This is one of the last little theorems on that worksheet where we take one polygon given to us as similar to the second, and the second given to us as congruent to a third, we are then able to prove that the first and third are in fact similar. And that's what we're going to do strategically with our third triangle here. We're going to build triangle XYZ to build that bridge such that it does connect ABC and RC together through similarity. So what we need, though, for our polygon similarity postulate is a positive quantity, right? Think about back to the postulate, what it said. We're given a polygon. Well, we have polygons to work with. We have triangle ABC and triangle RST. But in order to work with those polygons, we need a positive quantity K. Well, we can produce that with our definition of ratio. How we do that, and we guess this is where we're going to be strategic, is we choose a value from our second triangle, which is the length of RS, and we're going to ratio that with a value of our first triangle, which is a corresponding side, again, strategically, AB. So we create a ratio out of the two sides, RS and AB. And when we do that, we produce a positive quantity. Now, why do I know that's positive? Because our side measures of our triangles are measured positive, and that means the ratio of a positive to a positive will result in a positive quantity, which means with this K value, we can now produce our third triangle, triangle XYZ, by using the polygon similarity postulate. So let's take triangle ABC. We only need to scale one of the two triangles, and we're going to scale triangle ABC. So I take triangle ABC, that's our given polygon, and our and our value of K, which is by definition of our ratio RS to AB. So we take this positive factor K, and we scale our triangle ABC to produce this second polygon here, or really this third triangle in our case, triangle XYZ, such that these two are already similar. And that's what our polygon similarity postulate allows us to do, right? It seems obvious to me. I can take my first triangle, scale it by this positive value K, and it produces this second polygon that is similar to the original that I have constructed with. Now, what does this mean for us? If we know that these two triangles are similar, then right off the bat, we know we can tap into the definition of similar. And so there's a couple things we want to grab from that. The first thing is all our corresponding angles are going to be equal, which means the measure of angle A is equal to the measure of angle X, and the measure of angle B is equal to the measure of angle Y. So take a look, right? We've got our diagrams then denoting that equal relationship between our angles. Now keep in mind what we were given originally about our setup. We already know something about angle A and angle B. They're equal to angle R and angle S respectively. And so we're going to use that information here in a moment as we tie in triangle XYZ to triangle RST. Now to finish off with our similarity here, there's one other thing that we remember about this. That is, there's a scale factor between these two, right? By definition of similar, we can produce this ratio of a value of K. So this is a scale factor. And that's how we scaled our triangle in the first place, which means we took the side length of AB, right? This is some sort of value to it, and we multiplied that side AB by the scale factor K, which then produces this side length XY. So a critical statement is right here in the middle of the sentence above. XY is equal to K times AB. Now, in reality, we can continue this same thought for the other sides of triangle XYZ. I could say that this side is really K times BC. I could say this is K times AC, because that's really what's happening. We're taking each of the three side lengths of our triangle ABC and multiplying it by that scale factor K to produce the three side lengths of our second triangle XYZ. All right, so now what we have by our polygon similarity postulate, we have similar triangles between ABC and XYZ. But there's something else we want XYZ to do. We want it to be congruent to triangle RST. Well, it is. See, the thing is, we created our value K strategically. Okay, we created K, remember by definition, such that K is equal to the ratio of RS to AB. Now, with a little bit of algebra work, what we can say then is, right, multiplying both sides by AB, we could say that RS, the length of RS, is really equal to K times AB. But do you recognize that statement there? K times AB is an expression we've seen before. K times AB is the same as the length of XY in our triangle XYZ. Well, if XY is K times AB and RS is also K times AB, then what do we know about those two side lengths? They are the same, which means we can come down here and mark our sides XY and RS equal. Those are equal in measure. And with transitivity of equality, right, we were given that angle A is equal to angle R and that angle B was equal to angle S. But because of similarity between triangle ABC and triangle XYZ, we also know that angle A is equal to angle X and angle B is equal to angle Y. So then using transitivity, we know that angle X and angle R are equal and angle Y and angle S are equal, and thus we can conclude congruence between these two triangles, triangle XYZ and triangle RST. So we now have congruence between these. So let's bring these guys together, and we can officially conclude now that triangle ABC is in fact similar to triangle RST. Here's why. Because we produced triangle XYZ to do two things. It is, by construction, similar to our first triangle ABC. And with our angle side angle congruence, it is congruent to our triangle RST. Which means using that theorem we saw on a previous worksheet where we have one polygon is similar to a second and the second is congruent to a third, that means the first is then similar to the third. Okay, and that is what we proved previously, and that is what helps us carry us into the end of our proof of angle similarity. So remember, go back to what we were working on. We were working on proving this. We now have angle similarity as a viable shortcut in triangle similarity principles. So when you encounter two triangles such that two angles of one are in fact equal to two angles of the second, then you know that those two triangles have to be similar. And because of that, you can tap into the definition of similarity. We know then all the corresponding angles are equal and the corresponding sides are proportional. And that's what you're going to see unfold on your worksheet with the angle similarity. So diving into your worksheet, make sure you are working on that. If you do come across any questions on that, you are not to hesitate to email me. And be on the lookout for ways to show that two angles of one triangle are equal to two angles of another. Because when you can do that, you then arrive to similarity with our newly proven theorem, angle similarity. So with that, we are at the end of our lesson. So be good and do good.